For making this realizationable, 50 passengers will leave per pod, and every pod will leave, one pod will leave every minute in our station design. Besides this, the Delft Hyperloop made a European Hyperloop network where all the main cities are connected to each other. This process was done by an iterative optimization process where future demand, cost per passenger kilometer, and link distance were considered. So, what are we going to tell you today? We're going to give you a brief overview of our station design and our pod's interior. Here we will discuss the security, the airlocks, the sustainability, and the location of the station. Then we take you into a ride into the Hyperloop, into the European Hyperloop network, where we tell you all about our safety considerations and the vertical alignment of the tracks. So, let's start at the station at our own capital, Amsterdam. We decided to expand our developing business part of the city into an international hub. This hub will connect trains, buses, bikes, and trams into our Hyperloop network. Due to the quality of the soil and the over-occupation of the underground space, we decided to put the station on top of the Amsterdam South station. So, the entrance of the station will be on the street level. There, the passengers will encounter the security procedure. However, it would be such a waste of time to spend an hour at the station passing security, as you do at airports, as it will damage a core Hyperloop advantage, which is a short travel time. For this reason, we decided to propose a security procedure that considers an ideal passenger flow, so that one pod can leave every minute. Yeah. Due to the vacuum environment and the high density of people at predictable times at the station, we think it's necessary that a security procedure will be in place at a station. The recommended security measures include passenger screening and luggage screening, as well as security staff, as measures that are unavoidable to implement at a Hyperloop station. Besides this, closed-circuit television in combination with artificial intelligence could be used to detect, for instance, suspicious behavior. Besides this as well, the commercial interest that airports have to make passengers spend an extended amount of time at the station should not apply at the Hyperloop station, so that door-to-door travel time will be as short as possible. However, if we implement all these measures, it would mean that the security procedure, the efficiency will still be limited. So, to overcome this problem, we partnered with Hyperloop, which is a leading company in the industry of airport security, to see how we could solve this. As you can see in the picture, we envision a future where luggage and passenger screening could be combined, so that two important aspects of which have a big limitation can be reduced, which are space and time. So if the technologies continue to be developed in the screening technologies, in the end, the passenger flow can in the future be increased more and more. So now I will hand it over to Puck, who is going to tell you all about the station design and the interior of the pod.
Yes, is it on? Okay. All right, thank you, Annemiek, for telling us about the security and taking us through that. And now I will take you through the rest of the passenger experience. So our passengers start at the corridor on street level, as Miek mentioned previously. In this corridor, the passengers can encounter small shops, some waiting areas and bathrooms, but most importantly, from here they can use the elevator or escalator to go to the Hyperloop station. The elevators and escalators are specifically designed to improve the security of the station by making it impossible to reach the Hyperloop station from the train station below. The Hyperloop station consists out of 2 levels above the train station, and these levels of platforms are divided in 2 halves. Since we designed a dead-end station, in this case, the vehicles will arrive from the east. They stop for the first time in the northern half of the platforms, where passengers can alight the pod. Then the vehicle will continue into the tail, reverse direction, and go into the southern half of the platforms. Here, the passengers can embark the vehicle, and then the vehicle will continue in the same direction that it came from. While designing the infrastructure and this station, we took special care to consider the safety, feasibility, and sustainability of the design. By using modular design on some of the structure of the building and the tubes, we allow for easier construction and even implementation in different locations. Besides that, we designed the roof specifically with a consideration for sustainability. We integrated solar cells, which help to partly power the system, and the shape of the design is made to maximize the natural light inside of the building. This allows for less power consumption to operate the building. Finally, the shape of the roof is optimized for water collection, which can then be reused. Besides using sustainable materials, the components, structures, and services inside the building are designed for easy and efficient maintenance, operation, and reparation. For example, by linking material passports with building information modeling, we can keep a database of all the materials and services in the building. Then, by using Internet of Things, we can monitor all of the performance of the materials and assess the life cycle of the materials and the services. Once the passenger has reached their platform, it is time for them to board the vehicle. Here, a crucial aspect is the airlocks of the station. These airlocks should allow the passenger to safely embark and disembark the vehicle without encountering the pressure difference. We compared 3 different airlock designs, and we decided that for our station, the side bridge doors would be the best option. The side bridge doors consist out of bridges that connect straight onto the vehicle and therefore connect the atmospheric pressure at the station with the interior so that the passenger can safely board without any problems. The bridge connects onto the vehicle using hooks and seals inspired by space station docking systems. By using this kind of airlock, we are using a higher construction cost, estimated to be about 14 million for our specific station design. This is more expensive than some of the other airlock designs. However, there are 3 main advantages to this design that made us choose this one. The first one is that these are the most space-efficient airlocks that are available currently. And since space is very limited in a city like Amsterdam, it's very important that the station is as compact as possible. Besides that, by using these type of airlocks, each passenger saves about 30 seconds per operation, which, with the value of time, is an extremely valuable characteristic. Besides that, finally, when using these type of airlocks, the vehicle itself doesn't have to undergo as many pressure cycles, which extends its total lifetime. Now that our passenger is finally safely on board of our vehicle, we can explore the interior. It's very important that the interior is and feels comfortable and safe for our passengers. And Delft Hyperloop already has many iterations of interior design under its belt. This year we expanded upon it again to improve a little bit. Our interior is made up out of private sections, a social section, and a group section, fitting in total about 50 passengers. Using these sections allows us to give passengers the choice to either sit socially and talk to their friends and family, or sit privately and work, for example. Our interior is made up out of modules for each row of either doors, seats, or luggage racks. By using this kind of modular design, we make the complete interior design more feasible, flexible, and manufacturable for the future. In the design of our interior, we designed specifically with light colors, round shapes, and natural materials to make the passenger feel as safe and comfortable and calm as possible in a fairly limited space. We designed the chairs specifically for a safe and comfortable seating position, and there's some space at the bottom for luggage. Then the merged side-by-side seats are a space-efficient solution to seat people, either socially next to each other or more individually separated by an armrest. We also added luggage racks so that passengers can easily and quickly get rid of their bigger suitcases. The sectioning in the wall that you see in this picture allows us to give each passenger a personalizable space with their own light, info screens, safety panels, and charger ports. Altogether, our aim was to make the interior feel as safe, comfortable, and practical for every passenger. And now that we've gone through the passenger experience, I'm going to give the word to my teammate Stavros, who will go with you through the complete system.
Thank you, Puk. So, standardization and safety are an important aspect for the future implementation of our system. Delft Hyperloop developed last year a general safety framework in order to use it for future standardization and implementation of the Hyperloop. A hazards and risk assessment has been conducted for the overall system to assess what is the most critical components of this system. Safety packages were introduced in this safety general framework in order to achieve level of safeties that are similar to the one used in the aviation industry, which means that the goal is to have a safety which is equal to 0.06 passengers fatalities per 1 billion passengers. The safety packages include fire safety, communication, emergency evacuation, and perceived safety. Now that you've discovered the interior of our pod and the interior of our station, our trip can begin. An important aspect to assess is the vertical alignment of our track. In collaboration with TuckRail, we developed a guide to help decision makers get insights in the trade-offs for each vertical alignment, whether building the Hyperloop tracks underground, on surface, or on pillars. The different parameters that were considered for this comparison are listed here. The first 5 are for the determination of the direct and indirect effects. The nature conservation, aesthetic, and emissions are crucial for the sustainability of the project, since it's essential to assess how the vertical alignment would affect the biodiversity, the landscapes, and also the emissions over all the life cycle. Additionally, the travel time is also an important parameter. Different vertical alignment might have different length, hence different travel times, so these also should be considered in our comparison. Finally, the Hyperloop infrastructure can be used to lay down other utilities in parallel to it. However, this is not also always applicable for all vertical alignment, which also should be assessed in the comparison. The other 6 parameters are for the determination of costs. As we all know, the Hyperloop requires a lot of resources for the construction and implementation, and these resources vary per vertical alignment. Whether building the Hyperloop underground, on surface, or on pillars, our construction, maintenance, energy requirement, land use, and protection costs all vary, and should also be considered in the comparison. To apply the guide that we developed, we conducted a case study to assess what is the best vertical alignment in a specific section of a corridor. The chosen corridor is the one linking Amsterdam to Brussels. Several iterations were performed in order to assess what is the best horizontal alignment linking these two cities. The iterations were to make sure that the horizontal alignment considers the horizontal radius of the track while also considering the natural protected areas. And this is the horizontal alignment obtained. After applying the guide that we developed, the above ground was found to be less costly in terms of maintenance and construction for this specific section. However, this does not mean that this choice was to adopt the above ground solution, since the underground solution and other parameters should also be taken into account for this. The effects should counterweight a 1 billion euros difference in present value over 25 years of implementation and construction operation. These effects are monetized using the preferences of the government and the people. All in all, Delft Hyperloop has conducted extensive research and designed several components of the Hyperloop system. We are working towards the standardization and future implementation of the Hyperloop system. We strongly believe that the Hyperloop community should cooperate and coordinate all together, share knowledge on platforms such as hyperloopconnected.org in order to achieve our shared sustainable goal. In the future, we'll be working on the safety, energy requirements, and also technical feasibility of the system. You're more than welcome to join us at the stand to check our AR, scale models, and VR, and ask us any question you have. Thank you for your attention.
Okay, thank you, Delft Hyperloop, for such a lovely presentation. Now we're going to move on into a quick round of questions. So if anyone has a question, please raise your hand, and I'll walk over to you, and I'll hand you the mic. So any questions, anyone?
Hello, good afternoon. Wouter Perry from ACOM. You might have heard some earlier questions from my side. First of all, thanks for the very good presentation. I really like to see how you've built on the experiences from earlier Hyperloop teams and keep involving and evolving actually the good work. I'm not sure if I should ask the question to one of the three of you, but this is about something I read when going into the papers, and it's actually about the maintenance of the Hyperloop. You've elaborated on that topic a little bit in the presentation, but I'd like to ask, or actually tell first one thing and then another thing. You might remember that in terms of magnetic levitation, Transrapid in the past has also built together with Siemens a system that really goes forward, not in an atmosphere without air or with a simple amount of air, but using the same type of ideas to go forward, propulsion. You might also remember that in 2006, I think 22nd of September, there was a big accident in Germany, in Latten, where a maintenance vehicle was involved. How are you going to prevent that any maintenance activity does harm to the safety actually of people in the pod?
So thank you for your question. The first thing that we envision in our system is that first we have 18 hours of operation for the Hyperloop system. So then we have the rest of the day to maintain and do all the required information. And the main point that we considered in our safety framework is that there is always communication with the internal system of the tube through Li-Fi light fidelity system. So when you have always a connection between the pod or the maintenance pod with other systems, then it's very less probable to have any accident which might avoid any problem in the future. So this is kind of, I'm not sure if I answered your question. If not, then we can elaborate more.
For sure answered the question. That's already good. I like to go into the topic in more detail, but not here. But it's really good. So thank you for your answer.
Perfect.
Thank you. Any other questions over there? Yeah, okay.
I'm Michele from the jury group. Thank you very much for your presentation. Very impressive work. I have basically two questions. The parameters for the operation, I didn't see them, or maybe it was too fast. If you could repeat them or explain them to me, speed, etc. And the other question is, you mentioned about this 1 billion NPV thing. Could you explain a little bit how you reached this this value, and what is the work behind it, please?
I'll take the question too. Thank you for your question. So for the parameters of the different aspects, we have all the parameters. 1 second, since we have a lot of information. So these are the main parameters for our Hyperloop system. You can see that we have the mass, the accelerations, the speeds, for example, 1,080 kilometers per hour, and also the blockage ratio for the tube, which means that this blockage ratio prevents any problems with the shock waves in case of reaching this speed. I'm not sure if you need more information than this. We can. Okay. Then for the 1 billion net present value, we also have it somewhere. 1 minute. Okay, so we reached it. So when we analyzed the difference between the two vertical alignments, the first option was one between on surface and on pillars, while the other one was the underground option. So the different parameters that were included were only the common things not common things between the vertical alignments. So the levitation system are not included in the analysis, since it's a common thing between the 3 vertical alignments. So you can see here the different numbers that we have, and they are estimated for each aspect of the construction, maintenance, and protection, and all other elements. So we have them here, and for the specific section, we considered the construction costs and maintenance costs yearly to obtain then, by considering an interest rate of 4% as per the EU requirements, to obtain the net present value, which is here, estimated at 524 million, but it's a range of it's an interval since it's an estimation, so this is the 1 billion difference over 25 years of operation. I hope I answered your question.
I think so. I will check out the picture I took, but I'm sure you are there. Okay, I have another question then. About the sustainability and the energy use. What is the idea, what you were thinking about this? The use of renewable energy or things like this. I saw you have solar panels, etc.
Yeah, I think in the design of the station, as well as the design of the infrastructure, so the tubes, we mostly consider solar panels and solar cells pretty much everywhere where we can to partly power the system. Yeah, I think that those are the main things. I think if in the future like more sustainable methods are going to be more mainstream, then we could also apply those. But for now, we're especially considering solar cells on the station as well as along the tracks. And since we have quite a long track, we have quite a lot of surface area for solar cells as well.
And did you calculate how much you can cover with the solar cells? Or?
I think we did of the alignment, yes?
Yeah, for the vertical alignment, we have the width of the tubes is 8 meters, so we considered with the curvature that we can put 4 meters squared per linear meter of track. So that's what is the area of the solar panels on the tubes.
And I think in our report we also did a calculation on like the intensity of the sun in the region that we did a case study for, and then from that we got a kilowatt hours as well, but I don't have it memorized at the moment, sadly.
Thank you. Carolina, Lens Labs, also jury group 8. My question relates to the vision and you taking it forward. You've opened the presentation of the slide showing the European Hyperloop network, and you are in a position, you seem to be in a position, and you seem to have the ambition to make that your aim and that vision. So you have very specific designs and calculations for the Dutch route. is it correct to say that essentially this is your vision? And if so, do you have a plan on how to get there? And if you do have a plan, can you tell a little bit more about that? The question also comes because you're very clearly building, you're not reinventing the wheel and very much building on accumulated capital over the years. So could you tell a bit more about that?
Yes. Thank you for your question. It's a very good question. So this map was developed a few years ago by another team of our a previous team, and I think that of course we cannot we have a vision, and whereas we're all student teams, we only contribute to this 1 or maybe 2 years. So we cannot say if the teams in the future will adopt our vision in 10 years, or I don't know. But I think for the European Hyperloop network, I forgot what I wanted to say. Yes. We wanted to make it, the vision is, we have our vision in the European Hyperloop network as we are a country from Europe. But what we try to do in our designs and our work is to make the modular part of it and the standardization happening. So our safety framework focused mostly on standardization so that it could not only be adopted in Europe, but also, for instance, in the States or in Asia. And the same counts for the vertical alignment. We try to create a guide so that everywhere in the world you can use the guide and maybe change it to the destination where you're at the moment. So I think our main contribution is to try and make it a standardized.
Yeah, and I guess to add to that, I think as a student team, we need to dream big, and that's why in one of our first years, we decided to make a European network and not like a Benelux network or something like that. And we want to continue to build on it and continue to contribute to, as Meek mentioned, the standardization of it. But, you know, I don't think we can expect to start building tracks anytime soon. Does that answer your question?
That answers my question. Just out of curiosity, I'm going to push you a bit further, a step further. On which elements of the system did you have to go through the trade-offs? On which elements of the system did you have to say, well, the US will need this, Europe needs this, therefore we do pick this? Could you give an example?
So for this network, we mainly started from the origin-destination matrices of all the cities of using passenger flights data. So this passenger flights data is projected to 2040 with a 5% growth yearly. And these data were these OD couples, which are 640 couples for the overall network. We optimized these OD data, like the origin of people and destination of people, in order to maximize the kind of the societal value of the Hyperloop, which means that the optimization had the goal of to minimize the cost per passenger kilometer. So when we do this optimization, it was an iterative optimization process. We shifted the links to find the best way and how to make the network in order to minimize the cost per passenger kilometer. So the trade-offs were between the construction costs and the cost that the passenger is paying, actually. I hope I answered your question.
Yeah, thank you.
Yeah. To add to that, I think this method can be applied in any other region as well, by taking the same data, except for different areas. You can obtain the same kind of network and do that for the US or Asia or anywhere as well.
Okay, so if there aren't any more questions, that concludes this presentation and every team presentation for today on Hyperloop scalability. Thank you everyone for coming. One quick note, the technical jury will go to the sports hall to see the Hyperloop's prototypes at a later point. Right now we're going to continue with every presentation, so thank you everyone.